look at a t-test for a population mean. So we're still doing our hypothesis testing process. The big difference here is when we did our previous hypothesis testing process with the p-value in the traditional method, we knew our population standard deviation. That was what allowed us to use table E for our critical values. Here, in these types of problems, our population standard deviation will not be known. That creates a different family of curves known as a t-distribution, and those t-distribution values come from table F. If you recall, table F is based on degrees of freedom, which are sample size minus 1, and then it's also based on whether we have a one-tailed test or a two-tailed test, meaning right or left or two-tailed. So that's the big difference here. As we read through a problem, we look to see whether or not we know the population standard deviation is known. If it's not known, that means we will know the sample standard deviation, and we'll use that, but that sample standard deviation alerts us to use a different table or table F for our critical values there in step number 2. Quick little side note, because of the difference between table E and table F, we will not, I repeat, not do p-value method for our t-distribution. But you notice our test score down here is pretty much the same. Instead of a t-score, we have a z-score. It's our test, really kind of a cosmetic change. But our sample mean minus our population mean, here's where we see the difference, S instead of sigma. With our z-score, we add sample mean minus the population mean divided by our population standard deviation over the square root of our sample size. For our t-distribution, we won't know our population standard deviation, so we will know our sample standard deviation, which is our substitution, and then again tells us to use a different table or table F to find our critical values there in step number 2. Other than that, the table itself, I'll simply take a quick second and try and pull up here. But the table F, as you look at it, I'll scroll down so we can see it here. But table F has columns up here for a one and a two-tailed test. So we don't have to worry about dividing alpha by 2. We simply need to know whether we have a one or two-tailed test. That will allow us to look up what column here to use for our alpha, along with our degrees of freedom along this side. And then everything is very, very similar from there. So let's take a look at a few problems here that illustrate the difference between what we have been doing and our t-distribution. Consumer tested 18 bottles of a soft drink and found a sample mean of 15.8 ounces with a standard deviation of 0.4. So here, our standard deviation is of our sample of 18. So there's our sample standard deviation, or S. If the bottles are supposed to contain 16 ounces, is the consumer cheated test at the 0.05 level. So in step number 1, we will write our two hypotheses based on the fact they're supposed to contain 16 ounces. If they're being cheated, I assume we would all agree that means they're getting less than 16 ounces, so greater than or equal to, and we're going to test if they're being cheated, so our claim is our alternative. So that moves us on to step number 2. First thing I would note is we have not a right-tailed test, but a left-tailed test. Because of the less than left-tailed test. We also use table F for our critical values because of the sample standard deviation. Still going to continue to draw our curve here. Our curve for a t-distribution is somewhat similar to a normal distribution, just a little bit different. And then we have, it looks like we have 17 degrees of freedom, and alpha is 0.05. So we're going to go to our table here and find a one-tailed test for alpha equals 0.05, and then also our 17 degrees of freedom. So table alpha for a one-tailed test is 0.05. Down here to 17 degrees of freedom, I have 1.740. Notice that we're left-tailed, so that 1.740 is on this side, and because on the left-hand side of the curve, that is a negative number. So we shade the left-tail part of that, and then move on to calculating our test score in step number 3. So in step number 3, our test score is our sample mean, which is 15.8, minus our population mean, which is 16, our standard deviation, sample standard deviation, which is 0.4, and our sample sizes, which is 18. And as a quick reminder for our order of operations, I'll continue to put these in, and that will get us our test score. In this case, I believe our test score is about negative 2.12. That test score, to make our decision on the null, we bring that up here. It will lie to the left of negative 1.740. So in step number 4, that's going to tell us to reject the null. And in step number 5, since we said the null was incorrect, that means the alternative is correct, so the claim is also correct. That means there is enough evidence to support our claim. So in other words, we did enough research, or our researcher, whoever did enough research to verify that his claim the consumer is being cheated is correct here based on that statistical information. Okay, so again, we'll make this point here as we continue to move forward. Each section we go through, we have a little bit of a change in steps 2 and 3 here to different table to use, different method to use, different t-score, test score calculation, but ultimately it comes down to the same type of criteria as we move through here. So let's move on and try another one here. Ambulance company claims it responds to emergencies in less than 10 minutes. Sample of 12 calls had a mean response time of 9.6 minutes with a sample standard deviation of 0.9. Sample standard deviation, there's our spelled out word for word, tells us to use table F or a t-score, and we're going to test this at the 0.05 level. So our null hypothesis based on a mean of 10, and our alternative hypothesis based on a mean of 10 says he claims that they respond in less than 10 minutes, so less than, greater than or equal to, and he claims they respond in less than 10 minutes, so our claim is over here as being less than 10. So notice here we have again a left-tailed test. Alpha is 0.05, and if we have a sample size of 12, we have 11 degrees of freedom. We'll put our mean here in the middle. We'll put our critical value over here. That's going to come from the table. So we have alpha is 0.05, not 0.11. 11 is our degrees of freedom, or our sample size minus 1. So we'll go to our table. Alpha is 0.05. It's a one-tailed test. 11 degrees of freedom. We have a 1.796. We're on the left-hand side, so once again, our test score, our critical value, is negative. So negative 1.796 goes there. We'll move on to calculating our test score. Our sample mean is 9.6. Our population mean is 10. Our standard deviation is 0.9, and the square root of our sample size is 12. If we make that calculation, my test score is negative 1.54. Negative 1.454 lies to the right of negative 1.796. So since we're in the unshaded area this time, that is going to tell us to not reject the null. And since we did not reject the null, we're saying the null is true, which means the alternative is false, which means the claim is also false, or there is not enough evidence to support our claim. All right, so there's our process, again noting that our different table is used and we have a negative score on that left-hand side. We'll go one more time here. Job placement director claims that the average starting salary for nurses is $24,000. Sample of 10 has a mean of 23,450 and a standard deviation of 400. So our sample of 10 has a standard deviation of 400. There's our S, or table F, our t-score as our critical value. Is there enough evidence to reject the director's claim at the 0.05 level? H sub 0, our null hypothesis based on a mean of 24,000. Alternative also based on a mean of 24,000. Our job placement director claims the average salary is, so we're equal to and not equal to, remembering the equal to sign always goes with the null, but since he claims that it is 24,000, over here our null is our claim. So in step number 2, we'll note that first of all we have a two-tailed test because of the not equal to. It could be less than or it could be greater than. We have an alpha of 0.05 and we have degrees of freedom of 9. A sample of 10 means we have 9 degrees of freedom. So here I'm going to have both a positive and a negative test score because I have a two-tailed test. I'd say test score, I'm not critical value. I keep saying test score. But alpha is 0.05 again, and our degrees of freedom are 9. So we go to our table. 0.05 in our two-tailed column or row goes right here. So make sure we note that we had a two-tailed test. And we have 9 degrees of freedom, and that gets us 2.262. So on our table, or our curve, we have negative 2.262 on this side and a positive 2.262 on this side, which will then allow us to move on to calculating our test score. Our population mean, our sample mean, 23,450, minus our population mean of 24,000. Our standard deviation is 400, and our sample size was 10. That calculation gets us a test score of negative 4.35. Negative 4.35 is going to be well out here to the left of negative 2.262, which is going to tell us once again to reject the null. Again, we shaded based on the alternative hypothesis. Our test score lies in the shaded area. And that will tell us in step number 5, since we rejected the null, we're saying it's false. The claim is over here, so then the claim is also false, so there is not enough evidence to support claim. Now, just as a quick side note, notice up here that it says, is there enough evidence to reject the director's claim? For most of us, I'm going to say the easiest thing to do is continue to write as support or not support the claim, but you may see the answer key or may want to write it yourself. If there's not enough evidence to support the claim, there is enough evidence to reject the claim. So here we're actually answering the question that was posed up here. Is there enough evidence to reject? So again, you can make a choice here, decision. This is probably more straightforward for most of us since we've worked with that since the first day. But if you want to actually answer the question, we'll take this one as well. And again, we'll take either answer. This one's answering the question. This one is just going along our criteria we've gone through here to make life simple. And that covers our t-distribution. Again, noting that we have that sample standard deviation instead of our population standard deviation in previous problems.